our next speaker is Kristen Zarcone. I hope I'm pronouncing that correctly, from Case Western University. And she's giving a talk titled Build My Own MRI Scanner. Where do I start?
Thank you for the introduction. So like Dr. Cooley mentioned, I am Kristen Zarcone. I'm talking about building your own MRI scanner. Where would you start? I want to start off by sharing a little bit about myself. So I'm a third-year grad student at Case Western Reserve University right now. I started grad school about 2.5 years ago, or yeah. So when I started grad school, I'm working with Will Grissom, and we were talking about my starting project, what my thesis might look like. And we sat down and had a conversation, and he said, I have this really cool first year project for you. You're going to learn all about MRI. I want you to attempt to make a tabletop MRI scanner using as many open source resources as possible. This is a great way for you to learn about MR hardware, what it takes to actually put all the pieces of a scanner together and try to make it usable. And at the same time, for maybe the community, or have a broader impact on knowing how usable these open source tools are for someone who might not be an MR expert like myself. And so going into this project, I had no MRI background, very little hardware background. So I had been in machine shops before and been exposed to machining, but had not really had hands-on experience myself. I had a physics background from my undergraduate, so I had basic E&M knowledge, very basic like circuitry knowledge. And I was proficient in Python and MATLAB, which was super helpful in using a lot of these open source tools and kind of understanding what was going on underneath the hood, and if I wanted to make any edits in the implementation of this scanner when I was doing it myself. And so this talk is kind of organized into two parts. My overall goal is to just share my experience trying to make an open source scanner as someone who's not an MR expert and didn't have the help of many MR experts. Break down what the important parts are, share information I wish I would have known while I was doing this. And I have two parts. So the first is to just share what I did while I was attempting to do this. And then the second part is sharing other resources that I maybe didn't use or have been added to since I attempted this project. So first part, just my experience building a tabletop scanner and just seeing how far we got. So for the magnet design, this has already been touched on already. We use the Hallbach optimization out of the lighting group. I think a general like Hallbach has already been described. Normally you have these rings of magnets, and the radius of the rings tends to be shorter at the ends and larger in the middle, so that you can get a more homogeneous, stronger field in the center. We made some changes to this to make construction easier. And so we decided to not change the radii, just make essentially really long magnets and organize them in the array to make our B0 field. So we used 1/2 inch by 1/2 inch magnets, which Dr. O'Reilly mentioned earlier. Since we're in the US, we had to we couldn't order anything in metric. So I did the closest conversions I could, but we used 1/2 inch by 1/2 inch magnets, and we used 3 3-inch magnets, and essentially just made one long 9-inch magnet that was the length of our bore. We held these magnets in place using these 10-inch long acrylic tubes that we ordered, got them cut down to size on site, and then drilled holes on either end. We printed these end caps that were reinforced with fiberglass to hold the magnets in place. And then on the right side here, I'm just showing the simulated field maps that we got from the Hallbach optimization code. So for construction, I used OpenSCAD to generate STL files based on the Hallbach optimization configuration. And we used acrylic plates to hold our long rods in place. So instead of placing magnets in a slice, we had the magnets in these acrylic tubes that were then placed into the acrylic plates. And then we used these long copper rods to hold the plates together. Just some more pictures of construction. What we used, we needed to kind of shim the magnets into place because they didn't perfectly fit in the acrylic tube. So these are actually old face shields from COVID that we cut up because they were the perfect size for what we needed. And we just used a general like epoxy epoxied each side of the magnet, held it in with a wooden dowel, and waited till it dried, and then attached the other end cap. After we built the magnet, wanted to use a motion stage to map our field. We purchased this. We used a motion stage built by Image Guided Therapy. And then using a Lakeshore Gauss meter, we measured the field at 1 millimeter intervals over our DSV. After we did this, we noticed that there was a really wonky gradient across our fields. We wanted to know what happened. I learned after the talk what happened is that Dr. O'Reilly came, and because he's the expert, shared that I made an error when I was generating my STL file with the tilt of the angle in the inner ring. And since I started this project, they have added to their optimization that you run the code, and then there's an added component that will generate your STL files for you. So even if you're editing the holder, you at least have that as a checkpoint where you just take that code and alter it. So that would have been super helpful for me. But again, a user error that someone who, if you're trying to do this project in the future, you might not run into. So yeah, a great addition and something that would have been helpful. So we kind of called this step shimming the fields. We removed the inner ring with that error and remapped it. And then we had a really nice homogeneous field for what we had created. So this was our final magnet. We just had a very, simple bare bones. Just had one ring of magnets that all had the same radius. So moving on to the spectrometers, I used a GR-MRI, which was developed by my advisor and one of his master's students at the time. It generates short pulses. It's really easy to search for a signal, and Python based, so it was helpful because I'm familiar with Python and was able to get in it, and was already implemented in the lab, so it was easy to get set up for my purposes. For the amplifier, Mike Twig had created this gradient amplifier for us that we used as a transmit amplifier. We just used an off-the-shelf receive amplifier, this Mytech amplifier, and on the right, I'm showing the transmit amplifier that we used from Mike Twig. We used just a basic quarter-length passive TR switch that I'm showing here. And for a coil, just basic solenoid coil with 8 windings. And then the tune and match board I'm showing over here. And this is something that I had to learn how to do during this process because I had no experience with RF engineering or RF coil. So this is something that I had to learn how to do and was a valuable tool that I have since used very, very frequently. And so at the end of this, like Dr. Winter mentioned, we brought this scanner to London, so super portable. It fit in my advisor's carry-on luggage, and he flew it to London and got it to the convention center, and we had a little in-person demo, which was super cool. And we were able to get a spin echo signal both in lab and then after we got it to London, which was super cool. And this is kind of where we stopped. We had the time constraint of presenting this at ISMRM, and we were able to get a spin echo signal. Unfortunately, we didn't have time to add gradients and all of those things. So I'm going to kind of touch on that on the second half. Is if I were to do this again, maybe for an imaging system and not a benchtop system, would definitely use the Hallbach optimization tool again. This is a really great and comprehensive Hallbach optimization designer. Would definitely use the Hallbach MRI designer to generate my holders for the magnets. And yeah, you just use this open source tool for that. For the fabrication, we ordered our magnets from KJ Magnetics. They don't ship worldwide. So I just included a link for other magnets. You're going to need like a method to cut acrylic or a way to outsource acrylic cutting, a 3D printer, a way to hold the magnets in place, and a magnet polarity tester or a Gauss meter. And this was touched on earlier, but you want to double check the polarity of each magnet before you add it and close your system. We ordered a magnet polarity checker from Amazon, and then I just printed out a copy of my STL and then drew arrows towards north for all of my magnets. But as you saw in the previous talks, they had, used red or blue Sharpie to mark north and south. For testing, cozy measure was mentioned. I know this has been replicated a few times in the past. I have not personally worked with it, but there's a lot of great documentation for it. Gradient coils, again, I mentioned I didn't have time to add these, but I, in the past week, downloaded the software. The documentation for it is really fantastic. It's pretty modular and I think would be easy to modify to make your own gradient coils. I just used their Y gradient coil example. So it outputs this STL file of your gradient windings, of your gradient winding pattern. I imported that into OpenSCAD, and then using our resin printer in lab, just printed this 3D former. And so this was really quite straightforward to use, and I think a really, really great resource. And they also output a ton of nice plots, and you can really see what's happening, especially if you are more of a beginner and are trying to understand what's going on and what all of these different components are doing. So for the spectrometer, we used GRMRI. That was really great for a benchtop setup. I would probably use Marcos in the future with the Red Pitaya and the Okra One board. Again, the documentation for this is also pretty comprehensive, so that is a great tool as well. RF coils don't have to be super, super complicated. You can really just use a solenoid, either a 3D printed former or just kind of a cylinder, and wind your coil around it. Helpful to know CAD programming so that you can maybe make a former and print it, but not necessary. And again, another skill is learning to tune and match your coil. For amplifiers, this is something that I didn't really super get into in my own project, but have provided a few just GitHub resources that I either found on the open source imaging website or was aware of previously. And then finally, for shielding and EMI mitigation, there's really two main options. You can have a copper shield, which tends to get pretty expensive, or you can use some EMI detectors and coils, which I saw a lot of people implementing last year at ISMRM, which was cool to see and look at all of the different applications of that. Finally, just wanted to highlight some cool other open source MR projects. I know these were both highlighted previously, provided the links for those. There's a lot of really, really cool stuff going on in this space. And I think that a lot of it is pretty accessible for people that are not MR experts and maybe just have a background in science and are interested in this. And I think even in the past 2 years that I've been around and been kind of exposed to this space, there's been a lot of additions and great documentation added, which is really, really cool. So thank you. And again, it's by no means a conclusive list of resources or projects. I use opensourceimaging.org for kind of my be all end all of all the projects. It's really nicely organized and has a lot of great links to papers and GitHub resources and all of that stuff. So thank you so much.